Okay, well, welcome back. This video is a review of my solution for the two filter efficiency problems that I gave you to work on. Hopefully you downloaded the problems and gave them a good college try, and now you're reviewing your solution with mine. So give me a second to share my screen and we'll get started. There we go. So just a little bit of a review. Remember that filter efficiency is a kind of measure in the lab of how much suspended material we removed from our filter, from our water with the filter. And we do that by looking at average turbidity removed during the run. And we had to two kinds of calculations. First, the volume over time, because the flow rate can vary, and then the cumulative turbidity removed. So here's the first problem. Initially, the turbidity of the influent water was 83 NTU. And this is the data that we recorded in lab. Now, this problem looks different than the one that I showed you initially as an example problem. You'll notice that all the flow rates are the same. They're all 750 milliliters per minute, which means your volume treated per each time increment will be the same. You'll also notice the turbidities are much smaller, more in the range of typical output that we would see in the lab. Okay, so the first thing we want to do is calculate the volume treated. Now remember from our previous example, there is no volume treated initially. At time equals 0, the system's just started, so we haven't treated any water. Now remember, we've set our flow rate of 750 at the beginning of the cycle at time equals 0, and it's going to stay that way for 10 minutes. So that means 10 minutes later, the volume treated would be 750 times 10, or 7,500 milliliters. And then after 20 minutes, again, it would be 750 times 10, and it's going to be the same for all of them. That was a pretty easy calculation to do. So what's the total volume treated for the whole system? You would just sum that 7,500 milliliters 6 times, and you get 45,000 for the total. So in 1 hour, we treated 45 liters of water. Okay, so now let's go back and calculate our average turbidity. Now you remember that the average turbidity is the average at the beginning and the end of the time cycle, then times the volume treated over the total. So it's the weighted average. So again, at time equals 0, we have nothing. So what will it be at 10 minutes later? Well, we're going to average the two values at the beginning and end of the time interval, 4 and 5. We're going to multiply it by the volume treated, 7,500 milliliters, and then divide by the total. So I got 0.75 NTU. Hopefully you got the same. And this equation or this process will continue on. So at 20 minutes, I'm going to average the two values at the beginning and end of the cycle at 10 and 20. Multiply them by the volume treated in that 10-minute cycle divided by the total. And when you do that calculation, I got 0.83. And you continue this process all the way down. I won't show you every one of them. I'll just give you my values. When I get to the last one, I'll go show you what that one is. Remember, it's going to be the average at the beginning and end. In this case, 10 plus 11 divided by 2. Times the volume treated divided by the total treated. I got 1.75. Now remember, the average turbidity now is the sum of all of those. So if I sum those 6 values, I get 7.0. So the average turbidity for my 60-minute run was around 7 NTU. So how do I calculate my percent removed and my filter efficiency? Well, percent removed, remember, is the original turbidity minus the average over the original. Our original, I believe, was 83. So when you calculate 83 minus 7 divided by 83 and convert that to percent, I got a value of 91.6%. So this filter removed around 92% of the turbidity in the influent water supply. So what's our filter efficiency? Remember, filter efficiency is the volume treated, which in this case is 750, times the percent removed, which was almost 92%. So when I make that calculation, I get 41,205. You might get a slightly different number at the end, but that's okay. As long as you get 41,200, that's pretty close. So that's the solution to problem 1. So let's see what problem 2 has. A little higher initial NTU. This had an NTU of 112. And then here's some data. Now this data is really more typical of what we'd have seen in lab when you offered a really good filter solution. In that case, you'll notice right away that the flow rates are a little higher and the turbidities are a little bit lower. So that's a good solution for this particular problem. All right, so let's do the calculation. So let's do our flow rates. So the first flow rate is 0. So the first 3 are 1,200 milliliters per minute times 10 minutes. That will give you 12,000 milliliters for the first 3. And then we turn the flow rate down, you can see, to around 1,000 milliliters per minute. Again, times a 10-minute increment gives me 10,000. So those are my incremental flow rates over the 10-minute periods. And if you add those up, you'll get the total flow rate of about 66,000 milliliters or 66 liters. And again, that's more likely what we would have encountered in lab. So let's see what the average turbidity should be. So the first average turbidity we know doesn't exist because the run's just getting started. So what's the first one at 10 minutes? We're going to average our turbidities at the beginning and end of the cycle times the amount treated for that 10-minute cycle divided by the total. And when I do that, I got a value of about 0.0545. I want a few more decimal places because these are kind of small. All right, so what's the second one? So at this line here for 20, I'll average the beginning and end values, 0.5 and 0.5. That's easy to average. This is 0.5 times the volume treated, 12,000 milliliters, divided by the total. I get a value of 0.0909. Again, if you keep that up, these are the values I got at 30 minutes, and then between 30 and 40 minutes, and between 40 and 50 minutes. I'll go back and just show you the last one again. So if I want to do it at 60 minutes, again, I'll average the value at the beginning and end. The amount treated here, which you can see is a little bit smaller, it's 10,000, and then divided by the total. When I do that calculation, I got 0.25. So now I have my incremental turbidities. I simply just sum this stack up, and I'll get my total of 0.7455. So now what's my percent removed? Well, my initial turbidity, which was 112, divided minus my average turbidity over the initial. So this would be pretty high removal. In fact, when I do my calculation, I get 99.3% removal, and that's really good. So almost 99%, over 99% of the turbidity was removed by this filter. So what's the corresponding filter efficiency? Well, it's going to be the volume, right? The volume treated, which we computed as 66,000, times the turbidity removed, which was 99.3%, I believe. So that gives me a value of 65,561, which is really, really close, you can see, to the amount. So this is a pretty efficient filter for our purposes in lab. Okay, so let me know if you have any questions. Stop sharing my screen with you for a second. So again, the best way to get hold of me is through email. Just let me know if you have any questions. There'll be another video about how to do this. We're going to program a spreadsheet to do this for us as part of our next homework assignment. So look for that one. So until next time, be safe and take care.